So our last inverse trig function to look at is the inverse tangent function. And of course, the inverse secant, inverse cosecant, and inverse cotangent functions also exist. We're just not going to look at those, right? We're just looking at the sine, cosine, and tangent inverses. So now, the nice thing about tangent, of course, that you probably remember is that it had a period of pi as opposed to 2 pi, which made it a little bit easier to deal with. And it also had the asymptotes that basically separated the periods, right? So like between any two asymptotes would lie one period of the graph. So what we do with the tangent function is we just restrict its domain to be from negative pi over 2 to positive pi over 2, but notice the parentheses because negative pi over 2 and positive pi over 2 um, are undefined values of the tangent. So we have parentheses rather than brackets. So we limit the domain to that interval, and then we get a one-to-one function, which means it has an inverse. So as with sine and cosine, we have this equivalence relation. This is what this is called, an equivalence relation, where they have this double arrow. It's known as an if and only if statement. So what this basically is saying is that if x equals the tangent of y, then y equals the inverse tangent of x. And if y equals the inverse tangent of x, then x equals the tangent of y. So, and as with sine and cosine, we can also write the inverse tangent function as arctan, right? We can also call it the arctangent function, which is written as arctan. And sometimes that's useful because the danger with this notation is you can think of it as an exponent, right? So if you think of that as an exponent, it's really like 1 over the tangent, and 1 over the tangent is not the inverse tangent, it's actually the cotangent. So you got to be careful and realize that that's the notation for the inverse. So again, those two notations are interchangeable. So when you're asked to find the inverse tangent of x, you're asked to find the angle between negative pi over 2 and positive pi over 2, whose tangent is x. So we again have our inverse properties, which our textbook here is calling the cancellation properties, which basically says that if you take the tangent of the inverse tangent of x, you get back to x for any real number x. And if you take the inverse tangent of the tangent of x, you get back to x as long as x is specifically in this interval between negative pi over 2 and positive pi over 2. Because again, remember when we had something like this, like let's say we had inverse tangent of pi. We're not going to get back pi because pi is not between negative pi over 2 and positive pi over 2. So what we have to do here is realize, all right, well, the tangent of pi is really going to be the same as the tangent of 0, right? Because it has a period of pi. So whatever the tangent of 0 is the same as the tangent of pi. So this is really going to be the inverse tangent of 0 because tangent of pi is 0. But the inverse tangent of 0 now, this is asking for the angle between negative pi over 2 and positive pi over 2 that has a tangent of 0, and it's not pi, it's 0, right? So the inverse tangent of the tangent of pi is not pi, it's actually 0. So that's where this doesn't hold, and that's why you have to make sure that x is between negative pi over 2 and positive pi over 2. It probably is useful also to look at a little table of values for tangent, right? So here's the pictorial representation, the graphical representation. So there's your tangent function on the left, and the red graph, of course, is the restricted tangent function, which goes only from negative pi over 2 to positive pi over 2. And it's probably useful also to remember a table for tangent. We had said that you don't want to really necessarily memorize the the table for tangent, but it actually might help in this case. So when x is 0, the tangent of 0, you can see it right there, was 0. When x was pi over 6, the tangent of pi over 6 was 1 over the square root of 3, which could also be written as the square root of 3 over 3. The tangent of pi over 4, that's when x and y were both equal, that was 1. And then the tangent of pi over 3 was the square root of 3. So then what ends up happening is when you take these negative values, it just changes the sign of the tangent, right? Because tangent is an odd function. Because so remember, like the tangent of negative x was the same as the negative tangent of x. So if I put a negative in front of all these angles, then all these values just become negatives. So this isn't a terrible table to remember, to try to remember at least, for the tangent, right? It goes from 0 to square root of 3 over 3 to 1 to the square root of 3. as x increases from 0 to pi over 2. And of course, at pi over 2, it's going to be undefined. And if you look at your inverse tangent graph, what you see is since the original tangent function had vertical asymptotes at x equal negative pi over 2 and x equal positive pi over 2, this inverse tangent graph actually has horizontal asymptotes at y equals negative pi over 2 and y equals pi over 2. So you get, remember how we had done the end behavior with polynomials? You get this end behavior here. As x approaches infinity, inverse tangent of x approaches pi over 2. And as x approaches negative infinity, the inverse tangent of x approaches negative pi over 2, right? So again, you can see it. As you look to the right, what happens? Y gets close to pi over 2. As you look to the left, what happens? Y gets close to negative pi over 2. So that's important end behavior to remember, right? Because you have vertical asymptotes there. So then the other thing to do with the inverse tangent, of course, is to do what we did earlier, which was just evaluate, right? So again, the nice thing about inverse tangent is going to exist for any real number. So we're always going to get a value back, right? The domain of the inverse tangent is all real numbers, right? Negative infinity to infinity. So we're never going to have something that's undefined. So the inverse tangent of 1 exists, right? So if we look back at our table, when was the tangent 1? When x was pi over 4. So the inverse tangent of 1 is going to be pi over 4. What's the inverse tangent of square root of 3? Well, again, look back at the table. When was tangent radical 3? When x was pi over 3. So the inverse tangent of square root of 3 is going to be pi over 3. Now the inverse tangent of 20, we don't have that on our trig wheel, right? 20 never comes up on our trig wheel or in our table that we just looked at. So we have to do this one on the calculator. So what we'd say is inverse tangent, again, with that second tangent of 20 equals 1.5208. So this is approximately 1.5208. Right? And again, this is approximate to 4 decimal places. And then the inverse tangent of negative 1, well, again, looking at the table, tangent was 1 when x was pi over 4, so it was negative 1 when x is negative pi over 4. So this is going to be negative pi over 4. And then inverse tangent of negative radical 3 over 3, again, looking back at the table, well, tangent was radical 3 over 3 at pi over 6, so it was negative radical 3 over 3 at negative pi over 6. So the inverse tangent of negative radical 3 over 3 is going to be negative pi over 6. And then the inverse tangent of 0, well, this was not in our table, I don't think, was it? Oh, yeah, it was. At 0, the tangent was 0, right? So tangent was 0 when x was 0. So the inverse tangent of 0 is just going to be 0. Okay, so again, the main distinction here with inverse tangent is that you can take the inverse tangent of any real number because the domain of inverse tangent is negative infinity to infinity. So no matter what the input of the inverse tangent function is, you'll always get back a value. But just make sure that you realize that value has to be between negative pi over 2 and positive pi over 2 because that's the range of the inverse tangent function.